Um, okay, so I'm gonna get started now, since we already have some people. Um, yeah, so first, thank you all for attending, for joining us today. This is our second webinar in the webinar series that we're hosting as part of our space architecture competition. I'm not sure how many of you already attended the first webinar, but the purpose of these webinars is to give our participants some insight into space architecture to help them with their designs and to give them some ideas um, to use for their prototypes. And the main goal of this competition is basically to build an analog facility in Jordan, which is also one of JSRI's main goals. It's you can say it's our dream, and we're inviting you all to dream with us, and to add a bit of creativity to this. So today we're happy to have our second distinguished speaker. We have Asta Kacha with us. I hope I pronounced your name correctly. Is that?
Yes, that's correct.
Okay, good. So Asta is a space architect. She founded her own space architecture firm, which I believe was the first space architecture firm in Canada. And I'm so excited for you all to, and I'm also excited to hear what she has to say and to learn more about her work. So you can go ahead, Asta, and
thank you very much for inviting me, and I'm super excited to take you to this journey of space architecture. And I'm just gonna go and share my screen. I was expecting a little bit more students, but I think it's okay. It's a good start. Even if out of everyone, even one individual, I can motivate at least one individual today. So before I move on to the technical content of what is space architecture, I would like to quickly share my journey. I'm just gonna close this one. It is important to understand that what motivates us to pursue certain careers. So when I was just 13 years old, I went to this NASA Space Academy at Huntsville, Alabama Center. And during that academy, we were given a lot of different tasks. But one was very interesting to me, and that was to design something on the lunar base. And I designed a fuel station thinking that I might run out of the fuel while coming back to the Earth. And I got an award for that, NASA Lunar Contact Award. And in that moment, I got vitalized to pursue space architecture. Let me tell you, when there are no opportunities, you need to create them. And I was just one of them like that, because that time there was no opportunity into space architecture. There was nothing like space architecture. There was no stream like space architecture. And by the time I grew up, I was following this vision so strongly. And then slowly and steadily, I got into this field of space architecture. So you believe in yourself and you will get it further. And then since then, I have conducted different workshops on space architecture, lunar workshops, Martian workshops. And then I founded this also Aka Space Studio, where we are working on three very important things for this in the coming year. One of is a workshop, and another thing is we are also building a small scale space habitat prototype called NOAA, which is a next generation origami analog habitat. And then I'm also doing space architectural training through our expedition, which is upcoming in next January. So there's always a path, and there is so many more opportunities with the growing space sector into the field of space architecture. So I want to congratulate everyone who is focusing on this competition and trying to do something into this field, because this is going to come up very soon in the coming years. And we are in need of more and more space architects to explore this subject. So it is very important for us to understand exactly what is space architecture. Space architecture is not just space and architecture. It is a lot more than that. It is the practice of designing and also building inhabited environments in the outer space. Now, by this statement, what I mean is any environment that goes to the space and has a responsibility to protect the crew, that is the subject of space architecture. Space architecture is a big stream. It has a lot of different branches. For example, architecture design, engineering approach, psychological factors, sociology, industrial design. All of this come together to form the subject of space architecture. Now, it is very important also to understand that what are the different types of space architecture. Now, there are various types of space architecture. I think which that is something that I will go into the detail in the coming as we go further. There are two main approaches into space architecture. One is the engineering approach, and one is the architectural approach. Now, when we're studying engineering, it also has a different definition of how are we solving the subject, and same applies to the architecture. But how both of this plays into the role of space architecture is through problem definition. When we are, let's say, I think, I'm not so sure what is the background of all the students who are participating today, but I believe they're mostly from architectural background. Maybe you can enlighten me the background of the students.
Yeah, so most of them are architecture students, or they have already gotten their degrees in architecture. So yeah.
Okay, awesome. So let us see from engineering approach. That is a product oriented. Most we are focused on getting the product out. When we are designing an architectural project, we are process oriented. Now, for example, let's say that during your studies or when you're working during your internship, let's say that you got a project and the client wants to some sort of a residential house. So then you will explore different types of floor plans. We will start with the different kinds of floor planning, and then we will understand the client requirements. And then it is a process of the design. That is why we call it as an architectural approach. Then engineering approach is more of a linear analysis. It starts at the beginning of the process. And architecture is something that we also make a lot of adjustments throughout our approach to the design. And in the engineering approach, the workflow is from the start to the end, and it is mostly quantitative methodology. For example, we talk in numbers when we talk about engineering approach. Now, let's say that we want to design a space habitat. So then we need to also understand that what will be the indoor and outdoor temperature, how many mechanical joints we will be having, what will be the pressure difference. All of this plays a role in terms of an engineering approach. And when we come to architectural approach, it is more towards qualitative methodology. It is the quality of, let's say, when we're talking in terms of a residential house, it is the quality of that house. And in engineering, there is just one ideal solution, because when we are just concerned towards engineering approach, we are more towards scientific approach. When we are considering architectural approach, we are more towards art approach. So in art, we can have a lot of different sorts of solutions, and different decisions can be made. This is just a very basic of different approaches when it comes to space architecture. Now, what exactly is architectural studio approach? In this, I'm going to explain you how do we approach any project in our studio. Now, I think you are all in the beginning of your career of space architecture. Okay. So we start with the problem solving. We first have to identify the problem, and our problem statement will lead us to the definition of our mission, which will help us to understand the mission analysis. And after we understand what is our mission is about, we jump onto our human interference analysis. For example, what will be the functions that the crew will be performing. And then we go towards the habitat function. And that's when we start defining our interior design of our habitat and the material that we'll be studying and the following. So let us start with an example of, let's say that the biggest problem in the space industry right now is something relevant to lack of infrastructural facility. Now in US and Canada, there's so many flights which are taking up place for the tourism purposes. Blue Origin is also taking tourists. They're testing different analog astronauts to go to the space. Now, the problem is lack of infrastructural facility in space. This thing is also the problem of a space architect. So when a space architect sits to solve the problem, it will start with our mission. Mission as in, okay, so what do we do to solve the infrastructural facility? Do we build a hotel? Do we build like a crew quarters? What do we build up? That will help you. So then we find one possible solution of a problem. Let us come to the conclusion that maybe we should build some sort of a leisure quarters for the crew, where the tourists can go. They can just spend some time looking out of the window. Maybe they can stay for 2 days or 3 days of time. Okay. So this helps us to define our mission. So what is our mission now? Our mission is to send the crew to the space as tourists and allow them to stay for a period of 3 days and help them to have some sort of a leisure activity. Okay, now this is our human mission. The next thing we start working on is how do we approach our mission? How are we going to this space? Are we going in SN15 Elon Musk Starship, or are we going to NASA's rocket spaceship? How are we going to be launched to the space? This helps us to understand that how much payload capacity do we have, because when we are looking to transport something into the space or trying to build something into the space, it is very important to understand that how much capacity does our spacecraft has, because the bigger the payload, the more expensive the mission gets. So this mission analysis helps us to understand the boundaries of our mission. So after we understand our mission analysis, we have defined our mission, then we start working on our functions of the habitat. But before that, we start on defining the functions of the crew. So as I talked earlier, that let us say that our crew is going to look outside of the window. They will be trying to do some cooking experiments. They will be doing some microgravity experiments. They will be learned to using toilets. What else? They might even experiment a virtual reality for the space, some photography activities. Okay. Now this will help us to define the function of our habitat. So when we are designing our leisure module for the space, we start working on our floor plate. We start defining our floor plate. Okay. So now in this amount of the volume, we need to identify where our crew quarters will be, where we will have the bigger window, where will be the lab, where we can conduct microgravity experiments. And that is how we start designing our floor plan. And simultaneously, we also start to understand the engineering approach of our leisure module. Where our system engineering, where we will be having our ECLSS system, live control support systems, all of these things, where we will be placing, how their volume would be, how they will be functioning. So we work on these things side by side along with designing. And this is all a part of space architecture. So when in any future you're going to work in a real scale, real life industry, that's when this is how you will start defining your project from the start. Now, design process is very important. Especially in space architecture, we cannot jump onto finalizing the design without understanding the synthesis and the analysis and evaluation while we are making our design. Anybody can make a conceptual sketch, but it is very important to also evaluate our design. Now, let us say, I'll just carry on with this example of our leisure module for the space. Okay. Now, while we are designing, while we are understanding our mission, let's say that our mission analysis was that we want to build a leisure module in this space. Then there's also a process of evaluation. Now, for example, is it going to be a waste? Is it going to be a waste of the money? Yes or no? How it is going to support humanity for the space? Will there be any space policies that will be affecting government organizations? There are a lot of different factors that comes into the role. What would be the disadvantages of it? Maybe because when let's say that we talk about it as space is for humanity, but when we are producing a leisure module for the space, then only a certain amount of people might be able to go to the space. And that might create discrepancies. So there are a lot of things that we have to also evaluate when we're designing. When we're designing, we also have to evaluate that The sizes that we are going through, are they all making sense? Yes or no? What will be the lifespan of our module? 10 years, 5 years. We do also life cycle costing of our module. So there are a lot of different, and then let's say that when we are doing analysis. So when we have some sort of a basic conceptual design, especially at my studio Aka, we go through a lot of analysis. We go through thermal analysis, structural analysis, mechanical analysis, static analysis, and all of these different sorts of analysis are performed in different softwares. For example, ANSYS. Now, SolidWorks, ANSYS. Now, it is very important. Personally, I also feel this thing that I do not believe in doing just a conceptual design. I believe in the workability of our conceptual design. And that is why we have to do also the analysis. Now, I have come across many people who are doing this, just very good looking renders, architecture looking, very good looking renders, but there is no logic behind those. So when you're working towards a competition, you might also want to do some sort of an analysis that, let's say that you have your structural, you have a cylindrical structure, or you have a symmetric structure, whatever structure you are going, what are the form and the shape or massing that you're going with, you should also do some pressure difference analysis, how the pressure would be distributed inside that habitat. Now, also a lot of factors play into the role. For example, it depends upon what exactly you're designing for. Is it an orbital structure? Is it a space structure? Is it a Martian structure? Is it a lunar structure? Is it prefabricated structure? Is it going to be fabricated in space? Is it going to be ISRU, in situ utilization, resource utilization? These all things have to be considered while you are designing your habitat. Okay. Now, we haven't really explored ISRU because we haven't been able to really testify that in space. But what we have testified is prefab structures. For example, Apollo lunar landing module. What was a prefab structure. International Space Station that was also a prefab structure. So we have designed, built, and tested prefab structures. And then there are various companies who are coming up with some manufacturing in space. For example, there's a firm called Think Orbital. We did a project in collaboration with them. And what they were doing is they were transporting photovoltaic plates from Earth's surface. And in the space, they were trying to join this photovoltaic plates through magnetic collision, something like that was there. So now some people are also developing in-space manufacturing habitats. One of the core projects at ACA is also deployable origami. There has been a lot of research work done into inflatable structures. For example, one of the projects is from NASA called Transhab, where inflatable structures are basically like a balloon. So they go to space and they blow up with the pressure, with the help of atmospheric pressure system. But there are a lot of drawbacks also to that kind of inflatable structures because they're very hard to maintain. It needs constant air pressure. What if there's a puncture? There's also a lot of problems. There's a lot of harmfulness towards the space debris because there's a big problem of space debris in the space right now. And then what if some part of the inflatable structure goes bad? How are we going to replace it? It's very difficult. So we are coming with another concept called deployable origami. We are one of the very first people who are researching into deployable origami structures. Origami is this ancient art form of paper folding. When we were in the school time, we used to fold the paper. So we are exploring that. There are so many new techniques which are coming up now. So while you're deciding your project, it is also important to understand that what kind of project it is. I will just say it in this again, recall it. One is the prefab structures. Another is manufacturing in space. The third one is semi-prefab, like that will be just assembled in the space. And the fourth one, if you're going for a planetary habitat, then it can also be ISRU, in situ resource utilization, which can be mostly done using 3D printing technology for lunar or the Martian surface. So this is all we start doing when we are starting with our design process. Now, as I mentioned earlier, that there are different disciplines in space architecture. I'll start with the architectural piece. Now, when we are designing something for the Earth surface, I think most of you are doing it in terms of feet and inches or imperial system or metric system. But when we're designing for a space, we have to think in terms of volume and masses. Because now it also depends upon our project. When we are going to space, there is no gravity. So our anthropometry, for example, our body, it behaves in a very different manner. It has a free flow. We can reach to the roof, we can reach to the floor, we can reach every part of the habitat because of reduced gravity. We can move around so easily. So it is very important to understand that what is the flow of our body is going to be in the reduced or in the zero gravity, and how easy it will be for an astronaut to access the different equipments, to access the different systems, and maybe even furniture system into the habitat. I wouldn't go into the detail because I'm restricted to talk only towards fundamentals and foundations of space architecture, but this is one of the factors that plays into the role. Then we have our engineering. As I mentioned earlier, that it is important. Now, keeping the crew alive in the space is a part of an engineering process. We would need a lot of different systems. Now, to define our engineering problems, we first have to identify what are the challenges of our habitat. Now, let's say that our project is, let's say that you are designing something for the space, then there will be a lot of factors that will play into the role. For example, pressure difference, reduced gravity, no atmosphere, radiation, solar radiation, temperature difference. These are going to be a lot of different factors. When we are going to the moon surface, the lunar surface, there are going to be another sets of different challenges on the lunar surface. For example, isolation, lack of resources, day and night temperature difference, reduced gravity again. Then it is very far from the Earth, so it is not possible that in case of emergency, you can just come back to the Earth. It takes a long time to come back to the Earth. It's almost 3 days to come back to the Earth. So what do we do in case of emergency? There will be a various, then also, there was also one of the challenge that is quite a funny challenge, is that fear of aliens, extraterrestrial bodies. So we have to understand all sorts of challenges when we are working towards engineering approach. Okay. The third is the space sciences. Space sciences help us to understand, to solve the engineering problems. Then we have the industrial design. Industrial design help us to understand what kind of materials we will be using for our space structure or for a lunar or the Martian structure. There are various of materials that we use for the space. For example, carbon fiber panels, aluminum silicate, aerogel insulation. There are HDPE, high density polyethylene, plastic. There are so many different materials. Now, I have just some small suggestion. When you are looking to identify the materials for the space structure, let's say that you are looking for identifying the material for the outer space. Then you need to start understanding the materials for the aircraft. What kind of materials is the aircraft made up of? Then when you want to understand the materials that you can use for the Martian surface, on Earth, we have a lot of places where the soil is very similar to that of the Mars. So then we have to understand the soil type. And then we have to see that how this certain material will react to the type of the soil type. Then we have ergonomics. That is more towards sociology factor. Now, see, in humans, there's a thing called personal space. You don't even like when your parents enter your personal space. And you don't, so, and especially let's say that, I don't know how many of you have been living in this student dorms. Then there are a lot of arguments between your fellow housemates of personal space. Every human being has a personal space. And usually there's a 6-meter boundary from ourselves. That is actually our personal space. Anybody who tries to constantly interfere within 6 meters of ourselves, with certain period of time, we start to feel agitated. We start to feel irritated. And we do not enjoy that. And many of the time, people fail to recognize that thing. Now, see, when you are in your home, it is very easy to shut the door when you don't want your mom to sit in your room for a long period of time. And it's very easy to shut your door when you don't want your housemates to interfere in your room. But it is not that simple when astronauts go to the space, because I myself also an analog astronaut, and when you are in the space, you have no personal space. So it is so important. And at that time that you are also with other nationalities, you might even not like that personality of other persons. So then but then it is a design that will play the role of enhancing the human-centered environment. So during ergonomics, we just try to understand that we try to identify the different nationalities, the crew from the different nationalities, and then we try to see that how we can accommodate such an environment that will keep also that will also give them the personal space, and how we can enhance that. For example, you can just have your crew quarters. You can have a enclosed space when you are sleeping in the sleeping crew. So that is also to think when you are designing your habitat. Medicine is very important because when we are going to the space, we start to lose our muscle mass and our body reacts extremely different when we're in the space. There can be also some long-term diseases that can happen to us. For example, blood pressure, low blood pressure can also one of the causes. So it is important to understand that what medical emergency facility that also we would have in our habitat. And every habitat needs to have a med lab, medical laboratory. And the last part is the psychology. Now, let us say that any of you goes outside of your country and you are going to a different country to for your further education. You will go through a lot of psychological factors. For example, you will start missing your parents. You will be isolated. You might not able to make good friends over there. This all will start to affect you psychologically. Now, I personally do not know that what kind of projects are you guys working on. When we are considering space projects to the just to the level of the International Space Station, then we can think of a time frame between 3 months to 6 months. And very few determined astronauts get to stay for 1 year, but there hasn't been anyone who has stayed more than 1.5 years. Okay. Now, when we're designing for the lunar, it applies to the same 6 months to 1 year. But when we are going to the Mars, it is not possible to come back within a year. We will be staying there for at least 2 years, because that is when it is possible to have a return mission, because when the Mars orbit and the moon orbit is closer, that's when the time frame to travel from the Mars to Earth will become shorter. And that's the only time. So it is very important that our home, and also another thing is, when you are out from the Earth's surface, your habitat is your Earth. You cannot go in and out very quickly and very easily. Now, for example, here on Earth, let's say that you got into an argument, you just go for a walk, which is not possible when you're in the space, because in the space, your habitat is your home. So you must consider that this is what all you have for your crew members. And so we should have some sort of a very good, maybe you can enhance your space habitat through nice lighting design, or having some sort of an hydroponics or aeroponics into your habitat, something like that, that will keep the crew closer to the Earth's surface, which will give them Earth-like homeness. Okay. Now, this is something very important. I want you guys to just have a quick glance. Maybe you can also take a screenshot if you guys want to take a screenshot. This is important to understand the 3 different types of our missions. This is about human space planning mission. So have a look for it at 1 minute, and then I shall go on. Now, in my whole career, I had so many people asking me that, why do we need to go to space while we have so many things here on the Earth, where people are dying on the Earth? We have this climate change. We have so many problems here on the Earth. Why do we go to space? But let me tell you, understanding space helps us to understand our own Earth planet. When we're trying to understand the sun, we are able to make more efficient, and we were able to introduce the energy called solar energy, which is helping to fight the climate change here on the earth. When we had developed satellites for the space, it has helped us to understand the climate change and the population differences here on the planet Earth. When we're trying to understand lunar surface or the Martian surface, it helps us to understand that how our Earth was formed. How was the soil structure formed on the Earth? Because Mars is supposed to be formed before our Earth. It helps us to understand the evolution of the Earth. And I also personally feel that as a human beings, why we should not explore far and beyond, because we are one of the most intelligent social human beings. And I have this very strong belief that, all of us are so capable inside that we can, whatever we think, we can pursue that, we can find answers for that. And we are our itself this creation of this universe. We are also formed from this, when this earth was being formed. So we are itself our creation of this science. So why not we try to understand that? Why not we explore that? And also for International Space Station, because we have so much limited resources, and in space there are so many challenges. We have to recycle everything. We have to recycle food, water, air, everything. So because of that, we were able to develop much better recycling systems, which is helping us to develop much better recycling systems to protect our Earth's climate and the resources. And that is why we need to explore. Now, let us start with general. Continue and strengthen the cooperation between the spacefaring partners. Yes. This helps us for the moon when the people are landing and return. Now, you see one thing. I don't know how many of you have observed this thing. When we are planning to send a mission to the moon, okay, when we're planning to, let's say that we want to plan a crew of 4 to the moon, it is not the work of just one country or a few people. There are many countries involved in that. There are many nationalities involved in that. It brings the humanity together for just 4 people to be sent on the moon. So that is why also we need to explore. It is a cooperation. And this slide is not super important, but it is just so that why do we need to go to the moon? Why do we explore Mars? Why do we explore the asteroids? And why do we need to explore the space? Now, again, I don't know what kind of projects you are working on, but space architecture does not include only the projects outside in the space. There are various of subjects that fall under space architecture. I'm going to start with the Earth's atmosphere. We also have space architecture here on the Earth. How? Extreme environment habitats. For example, habitats under the sea, habitats in the Arctic, in the Antarctic region, in the desert area, in the isolated area, near to the volcanoes, or maybe near to where we have extreme heat. All of the habitats designed at these locations are also a part of a space architecture habitat. Now, this is just one example that of extreme environment habitat. Maybe you can look into MDRS station, that is Mars Desert Research Station, which is in Utah, and that is very isolated. It also falls under the category of space architecture. Then we also have a South Pole station, Vostok station from Russia in Arctic, in the very north. So these are all the part of space architecture. Can I just know that how far are the students in the design process? Have they already selected their project, or are they just about to select their project?
So all of the participants will be designing analog facilities. So this is very relevant to what they're doing. They're building a facility they're designing a facility to be built in Wadi Rum, which is a desert environment. So yeah, this is very relevant. But I think they're still working on the designs, but all of them are going to be analog facilities.
Okay, I'm very happy to hear about Wadi Rum, because we are also planning to conduct an expedition over there. So that was very relevant. Okay, now let us say that when you're designing an analog facility in Wadi Rum, it has to be mostly, see, you can use a lot of different sorts of materials. You can even recycle a container because the container will be very easy to transport, and also it will retain heat. And it is very easy to also modify a container and also to recycle. So when you're looking, most of the facilities that are designed for extreme environment here on the Earth's surface, they're either wood construction or either they are container construction with a very thick insulation if they're for the extreme environment, for example, north to the south. So this is something that you can think on. And it is very easy also to understand. It is also very easy because then we also have the availability of the resources that can go into the analog facility in the body room. Okay. Now, another category of space architecture habitats is the transfer habitats. Now, this is something that is very crucial because the transfer habitats, they are very small in size. SpaceX Starship, I cannot call that as we just got it here, but that is not actually a transfer habitat because it is a spacecraft. The habitat is only those space where the crew will be staying, the environment in which the crew will be staying. So let us start with our lunar module Apollo. Okay. Now in this lunar lander from the Apollo mission, there were 3 astronauts who stayed in that habitat. There was an ascent and a descent module. Okay. Now, one part of the module lands on the lunar surface, and that will have one of the biggest challenge. I will tell you one challenge from the real experience. When this one of the missions, one of the first missions, I think, when Neil Armstrong went to the moon, they had a problem. They got out of the lunar surface, and when they got back into that module, their suits was covered with a lot of dust, lunar dust, and that thing got inside of the habitat, and that is also a hazardous substance. So when you are designing for some sort of a planetary habitat and also for analog habitat for Wadi Rum, you need to have a dust mitigation system before your habitat. You are not, especially in space, you're not allowed to carry the dust from the extraterrestrial surface inside of the habitat because then it can harm the interior of the habitat. This is a very important point that NASA had missed while designing their first lunar module. So keep in mind, it can score you some more points. Okay, then we have this space shuttle orbiter. Also here, in the space shuttle module orbiter is also only where the crew will be transferring. That is only relevant to space architecture. And then we have SpaceX Starship. Also, I don't know how many of you have watched Inspiration 4, but even the Inspiration 4 from Netflix, they had this nice module where the crew of 4 astronauts, they were launched from SpaceX. And they had a toilet and they had a very small galley. Galley is a kitchen for space, but they had a very small minimal galley. And you can see that they had these big screens. And it is such a nice indoor environment, the Inspiration 4 module, that it looks very modern, unlike ISS station. I don't know how many of you have seen ISS from inside, but it's a mess. Everywhere there are a series of electrical items and everything is floating around, and somebody will get depressed if they're looking from Earth who is not an actual real astronaut. So then enhancing those kind of indoor environment is also part of space architects' responsibility. Then we have orbital habitats. The most relevant example of this is International Space Station. International Space Station just started with the Russian module, and then US module also joined in, and then we had a module from Japanese Space Agency, JAXA, and then we had an ESA module, and all of that come together to make International Space Station. You will not believe, but there has been more than 3,000 scientific experiments conducted at International Space Station. So it is a 10-year-old space architect's habitat. It is the most prominent example of space architecture, and I really suggest that there are a lot of resources available. There are a lot of astronauts journals as well, where astronauts have written their journals that what are the challenges that they're facing when they're in the ISS station, what kind of improvements can be done. All of those things are right there on the NASA's website. So you might want to look into those things because those are actual real life problems of astronauts when they're going to the space. And maybe those problems, understanding those problems will help you to make your habitat a much better place for astronauts. So International Space Station is something very important. And then we have the planetary habitats. Uh, you are seeing a very beautiful version of our one of our projects called Mangala on your screen. Mangala is a Hindu name or maybe Indian name for planet Mars. This was my first project personally. In 2018, I presented this project at ICS conference, International Conference on Environmental Space System. What you see on our web and what you see here is just a photographic thing. But the thing is, when we are working in the space sector, you're not basically allowed to publish everything that we have out on the web due to the copyrights issues. Okay, so, but I'm just going to take you to some details of this habitat, so it might help you to design something with ISRU. Now that it is a basalt fiber 3D printed construction, and we had this is the outer layer, it's basalt fiber, which is readily available on the Martian soil. So it is also kind of a Martian regolith construction. And then we have this 3D printed HDPE surface on the front, the white, which is helping us to keep our structure stable. And inside we have used aerogel insulation. It's a very lightweight form of insulation that it can be readily transportable to the Martian surface. And then basically we had a two floor. The top thing that you're seeing is the solar spotlight, which is helping to transfer the sunlight into the habitat at certain angles, and by reducing the radiation to provide the natural sunlight to the hydroponic lab which is inside. Now this habitat is equipped with for a crew of 4, and it has a volume of 360 meter cube. You require, okay, just a side information, you need 120 meter cube of volume per person, per crew member. That is a space, movable space that we require. So the habitable volume of the crew per person is 120 meter cube. And then there's also net habitable volume, and there's also some volume that your systems will be considering. So, and now I don't know how far are you going to go into your project work, but it is very important to do some volume calculations. And then there's a book called NASA Design Reference Index. Please, I'm just going to type in the chat, so this will help you do your research. NASA Design Reference book. This book it's like a building code for our space architects. This was a very first start to understand the basic regulations that a space architect can follow while they're designing the space. So when you are going through this book, you will understand how the body behaves in space and every detail of it, what kind of systems you would need, and everything is right just there. This can be your building code. Okay. So I really suggest to make the scale of your project more scientific. You should do some sort of a volume calculations, because even when we're designing for the space, we do volume calculations. Okay, now this is just a secret that I'm going to share with all of you. This is something very personal that I'm sharing from one of our projects. It is important to do at least, see, before you come to the conclusion of a design, you need to have at least 100 sketches of your ideas, because every idea will take you one step closer to your goal of your habitat. Okay. Now I want everybody to look at this diagram for 2 minutes and understand what they can get out of it. This is some sort of a floor planning. It's a bubble diagram of doing our floor planning first. And this is the very basics of a habitat. So spend 2 minutes and just have a look at it. Okay. Now, basically, this is also another secret. This is the basis of your whole space habitat floor planning. Okay. So you have an entrance, just like every other habitat, and then you have an airlock. You need to have an airlock because there will be temperature and pressure difference of the indoor environment and the outdoor environment. And airlock helps to stabilize the crew and get them prepared for the outside environment. So then you need to mandatorily have an airlock system. Now, following that, now these are different. You can see that there are two parts to it. One is over this way and one is over this way. Now it depends on every individual what they want to have. Now, when they are going towards this side, they can either have an ECLSS, that is life support system. For example, when I define life support system, it is basically water recycling system, air recycling system, and gray water recycling system, all of this recycling system, oxygen generating system, all of this would be into the ECLSS. And control room is just like an HVAC room, like a shaft. Even when we're designing for the earth habitats, we have this a mechanical room, we have this electrical room. So this is just like a control room where everything is being controlled. Then you can either go to, now you see, one more thing. Your habitat also needs to have this thing, silent areas and loud areas. Your habitat needs to be divided into this two separate areas, because in the silent areas, you would have your sleeping quarters or some important lab area. And in the noisy areas, you can have your this kind of systems where they will generate some sort of a noise. So we have to also separate these two areas into our habitat, which will enhance the performance of the crew inside the habitat. Okay. Now, when our crew, when the performance of the crew is enhanced, that means they are keeping up very healthy. So storage, then you can go to the private quarters, which is mandatorily, and you need to have a toilet near to your private quarters. But near to the toilet, you need to have a galley, because you will have a same plumbing system and electrical system for a galley and for a toilet. Let's say that even when we're designing an habitat for terrestrial purposes, then also we try to make sure that the toilets and the kitchen are sometime next each other, so that the plumbing lines and the electrical lines can be very short. So this has to be next to each other. And then near to the kitchen, I suggest to have a storage area, because storage area will help you to storage all of your food supplies, all of your liquid supplies, all of your medicinal supplies, things like that. And then near to the private quarters, it is advisable to have a recreation area, because then it is also important for crew to exercise. You can have some sort of a virtual learning space now in the modern days, or you can also have some sort of exercise area, yoga area, anything like that. And then you have the workspace. Now, the reason recreation areas between the workspace and the private quarters is because it is easy to access. Let's say that you're working and you want to have a break, then you can also easily go to the recreation area. Now, in the workspace area, you can include all sorts of the labs, chemical lab, bio lab, hydroponic lab. It depends upon you what your habitat is going to be functioning about, and that's how you can see. And then you have a med lab. Med lab is the medical lab, medical emergency. I personally suggest to have a medical emergency lab right next to the airlock. Now, let us say that you design this analog habitat for Vadidam, and then I think the goal will be also to build that analog habitat and also to have some sort of an analog stimulation. Is this the goal, or we are just doing a conceptual design?
Sorry, I was muted. Um, yeah, I mean, they're all designing an analog facility, and we already gave them some sort of like key key components that should be there to take into consideration when they make their designs.
Okay, awesome. So I think every space architect or every architect wants their project to be built. So it is important that Now let's say that you're designing this habitat and one day it get constructed, and then you will also have analog astronauts like myself or some other people will be coming to perform different experiments into the analog facility. Then let's say that they are out on EVA. EVA is extravehicular activity. And there are a series of experiments that we do in EVA. For example, soil testing study. We take some soil samples, or we go on some research work, or we can also do some microgravity experiment on the outside, or we can also do 3D printing outside. Something can be done outside as a part of an EVA. And then one of your crew members gets hurt. So you will bring that crew member back to the habitat. Now you want to make sure that your medical is easy to be accessible. So I really personally suggest that it is important to have your med lab next to your airlock system. So it is very closer in case of any emergency. So this is the basic floor planning that bubble diagram that we explore at ACA. And I suggest that you need to also have a lot of this so that you can have a better conclusion at the end. Now I'm just going to do a very quick glance from the beginning, concluding our today's session is foundations on space architecture. First, it is important what is space architecture. Then we have two different approaches. Then we move on towards how we understood today on how we would approach a project from the scratch, from the very much start. Then how should be our design process and what all things we should consider when we are designing, for example, different sorts of analysis, different sorts of evaluation, cost, budget. Now I will tell you something more, that you can design an amazing looking prototype, amazing looking habitat, but what if you don't have funds to build it? So it is extremely important to keep the budget in the mind. Now, let us say that you are all the students from Jordan, I believe. Okay. And you guys are participating in Jordan Space Research Initiative, which is like a research initiative, which is also maybe we should also think like this, that the people who have started this initiative, either they are self-funding it or either they are getting government grants to go on with this initiative. So as the leaders of this initiative, they have a lot of challenges to keep this thing going on. And for that, they will have a certain budget. Now, for an initiative research initiative organization, they will be acquiring government grants or there will be some private investors. It is not possible to have private investors because they will expect a return on their investment. So basically, they will end up with the government grants. Now, when we apply for government grants, my dear, it's not that simple. It's a very long process. You have to publish a lot of papers and you have to explain a lot of concrete reasons why this needs to be built. And then there's a series of political and governing bodies that will take place, and there is a time-consuming process as well. So there are always budget constraints. So if you guys are planning that your idea is going to contribute to a bigger goal to build this habitat one day and to conduct analog expeditions, keep the budget in your mind. And you need to start thinking of the budget right from the very beginning. I really think that, I don't know if this has been included or not, but I really suggest that maybe at this point, it will be very nice for the students if they can get some sort of a budget, because that will help the research initiative organization to establish parameters in future. So that is just an idea.
Yeah, we actually asked them to also give us cost estimates when they present their designs, because it is a very important factor, like you mentioned.
Yes. And then we understand when we're designing our habitat, there's so many different things that we need to just keep in mind and not just look from architect's perspective. And then this is, okay, I think I forgot to go through this one. Yes, I missed this one. Now see, when, especially in US and Canada, when you go with the government for the grants, you need to have a TRL and HRL, technology readiness level. You receive the government grants, there are mainly 8 points, and you need to acquire all 8 points or higher to be able to get the full government grant to support to build your prototype. Now, analog facilities are very small scale facilities, but when the structures that go to the space, they cost millions of dollars. So And it is not possible for any government to just give millions of dollars at once. Government gives their funds in different stages. And so these are the stages. When do you achieve certain points at what level? Because I believe that also building up our project and not just doing a conceptual study, we need to also understand that what is habitat HRL, habitat readiness level, and what is TRL. So the first one is this thing, habitation system research level 1. Level 1 is just like when we are trying to understand the human factors. For example, crew systems. Human factors as in, okay, what kind of functions humans will be performing, how long is for the mission, what we will need inside the habitat. All of these things is a part of this. When you try to understand these things and when you start reporting this thing, that is TRL1. It is not mentioned, but I'm telling this is TRL1. And this is TRL1 is going to be till the end of your all the TRL levels. Then you have the conceptual and the functional. Once you know that how your habitat is going to look like, that's when you start with your conceptual study, a feasible conceptual, a feasible concept, and that is about habitation design. What kind of materials you are using, what is your form, what is your massing, what is your volume calculation, what is the function. All of these things will be, and then understanding that how this habitat will be able to accommodate this function is all a part of TRL 1 to 4. Then you have this internal configuration, function definition, and location used of resource reduced scale models. This is the step when you build a small scale habitat. Unfortunately, I do not have any of my models right here. It is not here. Now we are in one of our project called NOAA. We are at a TRL 5, where we have done a small scale 3D printed model, and we are able to deploy and undeploy. This is where when you build a small scale, but small scale is not actually just a small scale 3D printer. It's like a human size of a habit that is called also small scale. And then you go to a full scale mock-up models. For example, maybe the best thing to know this thing is through Artemis mission. You can look into the Artemis mission of NASA, and then you can see over there that how they are building this Artemis modules, launch modules. They are a full-scale prototype. And whosoever is taking the contract, now there are some private companies who are also participating into government organizations to do this kind of things. Now, all these private companies, everybody is mandatory to go through this TRL approval levels. Then level 5, 6 is like when you are actually testing your full scale prototype and your full scale habitat, your design. And then the last is the pressurized habitat prototype testing. That is that now it also depends that if your habitat is going to be pressurized or not pressurized. Now, when you're designing for your body dump analogs, then you do not need a pressurized habitat. But when it goes to the space, then we also check. Now, checking all the engineering systems into the space habitat is a part of our testing of the technology, TRL 7 and 8. Just in case if anybody is interested to pursue your career further after this competition, then this is what you need to go through. These are some testing standards. And then we understand what are different types of habitats. If I knew earlier that the subject would exactly analog habitat, I would have gone a lot more into the detail of helping to understand all different types of analog habitats that we have here on the Earth, but maybe next time. And then we have transfer habitats, orbital habitats, planetary habitats, and then designing the floor plan. Okay, I think that's all I have to conclude today. Thank you very much for joining today, and I'm willing to help you with all your questions.
Yeah, thank you so much, Asta. That was very informative, and I learned a lot. I hope the participants, I'm sure they also learned a lot. Maybe just to, I'm gonna, yeah, if anyone has any questions, please send them in the chat. But for now, I would, like you mentioned, since you didn't know that this was focused on analog facilities, do you have any any points to mention? Are there anything that they should consider when designing an analog facility? How does it differ from regular space architecture?
Yes, that's a very good question. So let's say that when we are designing for Vadira, I would just like to conclude. Understand the direction of the wind and the sunlight. Where is because usually we receive the most of the sunlight in the east direction because the sun rises in the east. So when we are on the east side, we should have more of windows in our analog habitat. Because when we get up, let's say that when you wake up and when you see all the dust sky right in front of you, then you feel gloomy in the start of your day. So we should have our windows focused towards east, so we can have a natural sunlight right in the morning. And then also wind, the entry of the habitat is very important. When how fast, what is the wind direction, and what kind of storms do we have. The topographical study is also very important. And then as I say that even when we are designing an analog habitat, it is important to understand the personal space between the crews. We need to have, I don't know how long, let's say that we end up building our analog habitat, okay. So I believe that the smallest mission will be at least 2 weeks, from 2 weeks to 6 months. It cannot be less than 2 weeks.
Mm,
And another thing is, if we are concrete on our analog facility, then it takes 21 days to change a habit and 90 days to change a lifestyle. So then the expedition can be around 20 days to 90 days. Now, when we are looking for a mission more than 2 weeks, it kind of starts to affect us psychologically. So it is important that every crew, when they are going to sleeping, they are able to at least cover their beds with some sort of a partition, and they're not completely exposed. So there are a lot of things, there are small things that will help to enhance. And I really suggest that even when you're designing an analog habitat for Earth's atmosphere, why not we build something that looks like the space. We want to give a real life experience to our crew when they will be staying inside the habitat. So I really want everybody to research into how does the galley into the space looks like, how they are taking up the water, how they are taking up the food. So when you design the kitchen for an analog habitat, you should think that they will not be getting hot cooked meals cooked on a pot. They should have a challenge of having some sort of a pre-packed food, the
mm,
something like that we have in the space. So how it will be easy to cook such a food, how it will be easy to also clean. We should also think of resource management, because this habitat, analog habitat, will be constructed in isolation. It wouldn't be somewhere where there will be city area, right?
yeah.
So then you will be very limited to your resources. So this is a challenge, that with limited amount of water, how we can enhance our habitat, how we can recycle everything, what things we can have, how our analog habitat will function. Yeah, I think that's all I can conclude for today.
Yeah, thank you so much. Like Asta said, there are many considerations that also apply to analog facilities, like the psychological aspects and all of that. And she also mentioned the dust mitigation. I think that that would be very important to address that in your designs. Um, I was gonna ask you if you have any resources that you would recommend, but you already um, recommended that they check out the NASA
Yes.
design reference book. Do you have anything else that you would recommend? Any other
Yes.
reference?
Mhm. Now, see, I just we have to be very self-motivated to design something like this, and it's very important that whatever we are doing is the best thing that we are doing. We don't want to do some sort of an ordinary work. So how do we become best? We start understanding what is existing, and then what we will be doing to improvise it. So I really suggest that everybody to start with your research work with all the analog habitats that exist here on the earth. Go through every research station, see what kind of research work they're conducting, what kind of habitat space do they have, where are they located, what are the, and then do a SWOT analysis, strength, weakness, opportunities, like that. SWOT analysis is there. And then do a SWOT analysis for all of these analog stations. And this will help you to define very precisely on how you can be the best designer for your analog habitat. So
Mm.
be very motivated.
Yeah. Actually, we already provided them with a list of
Oh,
analog habitats around the world. So that's a good place to start. You can read about each facility and learn more about it and how um, if it would fit, if there are any elements that would also work for your design. But yeah, let's see if anyone sent us any questions. Not yet. Let's give them some more time. But yeah, thank you. I actually really enjoyed this, and I'm also happy that they got to learn not only about analog space architecture, but about real space architecture, if that's anything that the participants are interested in pursuing in the future. Yeah, it was really interesting. Thank you so much. And also, I would also like to thank the Moon Village Association for helping us host this webinar. And thank you, Giuseppe, for being our host today.
All right.
Yeah, I'm just gonna wait to see if there are any more questions.
And I think if somebody's feeling shy to ask a question right now, they can always mail me. I'm willing to support, because this is something that I get very inspired. And I also get very inspired when I help someone. So anybody can mail me to ask any question they have.
Oh, okay. Thank you so much. That's really sweet of you. And yeah, like you said, you were hoping we would have more participants today, but we are recording this session and we're going to send it to all of the participants. And they're also free to share it with other people who are interested in this topic. So yeah,
Okay.
thank you so much. I don't know, does this mean that no one has any questions? Should we wrap this up?
Okay. Awesome. Thank you, everyone. And
Yeah,
good luck with your project. Bye-bye.
thank you so much, Asta. Bye.